Presentation by Jim Head. Does he have any co-authors? Don't know. Okay, we are going to be hearing about eruption of lunar magmatic foams.
That's close enough.
That's close enough. Jim.
Thank you very much. I'd like to dedicate this talk and a lot of the conference, I hope, to the memory of Neil Armstrong, the first human to set foot on another planetary body 48 years ago today. So Neil was an incredible guy, a real pleasure to work with, total professionalism and competence. If you want to hear some Neil Armstrong stories, ask me at the end or buy me a beer, okay? So Neil would have been just really excited to have seen the kinds of things that we're looking at here and the characteristics of these units here. They're very unusual. He would have been the first to say, let's go explore these things. Let's go back and take a look at what we're seeing here. So these are, in fact, features that we interpret to be magmatic foams emplaced on the moon. And let me say the basis for this is an absolutely wonderful paper published in 2014. Sarah Braden and her colleagues, as part of the LROC team, if you students in there want to know how to write a professional paper, read this paper and copy the way it was done. It's beautiful, really well documented, et cetera, wonderful interpretation. So they looked at 70 small topographic anomalies and termed irregular Mare patches, up to 5 kilometers in diameter in the Mare. Really unusual features, most are on the near side. And they contain these irregular morphologies that are just quite unusual. That's something you just don't see typically on the surfaces of the lava flows with large regoliths. The floor is optically immature, few superposed craters, very few superposed craters, which suggest a really young age geologically. So the crater distribution, crater size frequency distribution ages are all less than 100 million years for the 3 largest features, which is really young. So they looked at these and then on the basis of this interpreted them to in fact to be late-stage volcanic eruptions on the moon. Now this has real implications, so it's very important to look at these things and understand what this is telling us. So basically the very recent 2-stage eruption and extrusion processes, which they envision, actually has, for example, in cross-section here, I've reproduced this. So you have old Mare surface here, but in the middle of this Mare surface, you actually have this rough area here, which they interpret to be a dike feeding a collapsed vent or lava lake. And then this smooth feature here, which is in fact, they interpret to be a later dike, which in fact is feeding the smooth irregular Mare patch here, these features here. So this is pretty amazing. And this, they say, apparent superposition relationships of these over the rough stuff and the optical immaturity of the hummocky unit and the young CSFD ages are all indications of very recent volcanism. So we've been taking a look at this to try to understand what's going on. The 3 largest, Koshi 5, Sosigenes, and Ina, in fact, all have ages less than 100 million years, and Ina itself is about 18 million years, which is incredibly young from a volcanic eruption point of view. Now, when we take a look at Harry Hiesinger's compilation of lunar ages, we know, in fact, this is a wide distribution. And if we look down here, for example, the vast majority of volcanism on the moon is dated to 3.9 to 3.1, but there's evidence from meteorite ages for volcanism, Mare basalts as young as 2.9, and evidence for volcanism from a stratigraphic point of view as young as essentially 1 billion years. And these features are way out here, less than 100 million years. So this is really amazing. And what this suggests is, of course, that if it's actually out here, late-stage eruptions suggest a long decline in lunar volcanism. This places strong constraints on, in fact, lunar thermal evolution, okay? Generation of basalts, literally at the present. So it's really important to test these things and understand what's going on. This is a perspective view of the topography of Ina. These are highs. It's really hard to make your eyes do that, but in fact they are. These are mounds, 2 to 3 kilometers in size, 50 meters deep, depression with low mounds, similar in appearance to surrounding Mare units, rising from a what looks like a very fresh, optically fresh and disrupted floor. So how do you produce these things? But we went back and take a look at this and try to put it into context to try to understand from a volcanological point of view how these things might have formed. So the first thing is that we observe with all the LROC data and also LOLA data that in fact Ina sits on top of what appears to be a shield volcano. In fact, this is it in topography maps, this is it in cross-section. You can see Ina is perched right on the top of this, this summit of this small shield volcano. If we take a look at essentially the height versus base diameter and the summit crater diameter versus the basal diameter, this fits right in with all the other Mare domes, if you will, as a typical summit crater. So what's the age of the Ina shield volcano then? Here's Ina. So we took a look at the dates in Cowdall in a GRL paper we had recently in and found that, in fact, the exterior here, the volcano itself is 3.54 billion years old. Okay, so that's typical Mare. It's right in the middle of the Mare peak volcanism period, okay? So the hypothesis is that this summit pit crater actually waited around for 3.4 billion years and then erupted again, okay, in this center part of this caldera. This is kind of unusual from a volcanological point of view. Nonetheless, let's press on and think about this. Let's take a look at the topography within the area here. This is the feature that I was just showing you. This is a topographic map from LROC Topography and Lola Topography. And you can see here it's characterized by essentially a marginal terrace in green here, and then an interdepressed interior like you see in the blue areas here. So this is typical, actually, of Mare, of essentially volcanic summit pit craters, as we see, in fact, in this view of Kilauea Iki in Hawaii. You can see, in fact, the crater itself. It's the marginal terrace around here and the depressed interior. Now, we can take a look at this one, much easier to get to, and think about what's going on in terms of the characteristic morphology. Well, as you're walking across the floor of this, as many of us have done many times, you can see, in fact, the characteristics. There's a macroporosity. The thermal boundary layer that's defining the top of the lava lake is, in fact, deforming and modifying, so you're building up a lot of pore space, what I'll call macroporosity. You can see this here at the edges, throughout the base. You can see it on these little mounds, these almost wrinkle ridge-like features, tilted blocks. You can get down inside of those. They're almost lava caves in some cases. So macroporosity is important, okay? So lava drainage and thermal boundary layer draping cause a significant amount of macroporosity. There's extreme vesicularity, too. If you look up closely, microporosity is also. The basalts are very vesicular. There's almost foams, and also a lot from the drilling, a lot of void space in the upper parts of these things that is actually part of the bubbles, not so much the thermal boundary layer variations. And you can see the combination of drained lava lakes of extreme macroporosity and microporosity. So we might expect this on the moon as well. So this is, again, we'll now turn to the characteristics of a lunar volcanic eruption, not a terrestrial one, although the vesicularity ought to be similar. And in principle, with a lunar vacuum, any gas exsolution should be operating much more efficiently on the moon than on the Earth. So all the macro and micro vesicularity that I'm telling you about from the Earth ought to be magnified, if you will, certainly should be magnified on the moon. So these are the 6 stages that we've outlined. Lionel and I did. There were 2 doorstop papers that we published in Icarus a couple of last year. Or was it this year? I don't know. Got it. Anyway, whatever. The bottom line is these first 3 stages, the dike propagation to the surface, the venting to the surface, the buildup of the shield volcano. Let's start with this one here. When the key thing is that when the eruption starts to wane, okay, so the overpressure is decreasing, the lava is slowing down, the crack is starting to close from stresses in the lithosphere. And so what happens then is that the ascent of the gas bubbles overrides or becomes greater than the ascent of the magma itself. The magma is slowing down, but the gas is exsolving. So this produces typically on the Earth a strombolian phase where the gas bubbles burst at the surface, and that's what we would expect here. When in fact the volume flux goes to 0, that is the dike stops, if you will, then you enhance the exsolution from H2O, and you build up a huge amount of gas exsolution, and you start building up a foam at the same time that the dike is squeezing shut, because it's no longer being overpressurized to get the lava out. So what we have here then in the summit crater in the lava lake is in fact a boundary layer underlain by this massive amounts of degassing and foam that's coming up from the subsurface as the dike extrudes. So let's take a look at this area here, if you will, and then go to the next one here, which is the same blow up. If we magnify to the lava lake, what we see is a thermal boundary layer here. That's this here, a macrovesicular lava lake crust, if you will. And then below that, we have, in fact, this area of magmatic foam buildup as the dike is starting to close. Dike closure squeezes the foam out, and then it cracks this crust. And the magmatic foam we interpret to come out much as you see here. So let's take a look at this in a little more detail and think about how this process might work, okay? So what you see here is a cross-section of that what we just visualized. We see these mounds here as these features here. And the first thing that happens is you, of course, have this macrovesicular lava lake crust, which is a thermal boundary layer of the cooling lava lake, if you will. And then the magmatic foam collects below the thermal boundary layer from the closing dike. Then you get flexing of the thermal boundary layer by the closing of the dike and the inflation, if you will, and pushing up of the foam layer. And that cracks the crust, and then, indeed, the foam extrudes to the surface and forms the mound, as you see here in the upper right. Now, this foam can be up to 95% vesicles, okay? It's really can be, we've calculated on the gas exsolution, it can be up to 95% vesicles. And finally, what happens when you erupt this into a lunar vacuum, of course, you get vesicles. It would be really interesting to hear if there was an atmosphere, but you get significant popping of bubbles in a vacuum, which produces a meters thick low-density soil, which may explain, partly at least, the morphological characteristics and the physical properties of these things. So let's take a look at what happens here then. So we have this macrovesicular lava lake crust. It's extremely porous. This is sample 15016, the famous seed belt basalt. This is not from here, but it suggests that this is 50% volume percent 50 volume percent of 1 to 5 millimeter vesicles. That's a really vesicular rock, okay? So if this is anything like that, then you can see what happens when impacts start to modify this. It's going to break things up, and you'll get a lot of sifting of the volatiles right into, of the soil right back into this very macrovesicular substrate. So this can keep the regolith from forming and maintain an optically immature surface in the area surrounding the foam. Now, when the foam comes out, of course, it's a foam, okay? It's like an aerogel. So this has huge influences, like a pumice, and this has huge influences on the ability of that substrate to retain craters and get an old crater size frequency distribution age. And so if we take a look at this and think about what happens, this is a pumice which has had an impacted, it's a hypervelocity impact into an experimental piece of, experimental impact into a piece of pumice, okay? And you can see here what happens. Basically what goes on here is that you get, in fact, like an aerogel, penetration into this and crushing of the substrate, not building of a crater like you do in a common, more solid rock. So this means that the energy, if you mapped out the energy here for a solid piece of rock, it would be, in fact, a crater that's much broader than this one is. So you end up, for similar energies, producing craters that are much lower in diameter, which will then yield a different frequency distribution, a frequency distribution which is deficient in large craters. That means it'll come out as being very young. So that's what we think it might be going on here. And in fact, when we take what we adapt the size frequency distribution based on the experimental configuration of how the diameters are decreased, we come up with dates that are much closer to what we see here of the volcano itself. So this leads us to interpret these deposits as actually being contemporaneous with the Mare, not billions of years younger. And we think that, in fact, the characteristics of the substrate here is what's giving you anomalously young dates, and that actually may not be young, it may be contemporaneous with the crater itself. Now, one of the things we can see here is that we've been dealing with Ina, which is a summit pit crater. So it's on the top of a volcano itself. What about when these things form in the Mare? Lionel and I outlined in this JVGR paper. You can see here in a perspective view, the late stage, out in the Mare, the late stage foams will come up and they won't be constrained by, in fact, this characteristic summit pit crater, but they'll just flow out onto the surface. So we might anticipate magmatic foams and thermal boundary layers on top of those out in the Mare as well. We think this is probably what's going on with a lot of the other irregular Mare patches. Now, as luck and serendipity would have it, we've been working with our colleagues in the People's Republic of China, particularly at the Macau University of Science and Technology, and they found these incredible features, which, I've looked at millions of pictures prior to Apollo 11, looking at Mare deposits to see how smooth we saw none of these things. Now, you're going to have trouble visualizing this, but the illumination is coming from this direction. These are not craters, they're mounds. So there's hundreds and hundreds and thousands of these ring mote dome structures is what we call them. There's a ring mote and a dome in the middle of the Mare, and they're distributed all over the place in Tranquillitatis, Serenitatis, and elsewhere. These things, in fact, we have a paper in revision in GRL, which will deal with the details of these. But the bottom line is that we think, in fact, these may be breakthroughs in these boundary layers, like you see here, to produce these ring mote dome structures where the mound comes out and then the thing subsides into the lava flow. So this may be evidence for these, in fact, foam-rich extrusions at the end of the major volcanic phases. So the bottom line is here that, in fact, magma foams are a predicted consequence of late-stage Dike emplacement events. They form an association with old lava flows, not necessarily in small shields. The physical properties are like an aerogel, and the superposed impacts are smaller, so it biases the size-frequency distribution towards smaller diameters and in fact, younger ages. And indeed, macro-microvesicularity is the cause of the regolith that seems to be very thin, we think, and also in terms of the enhanced the optical immaturity. And finally, this is, as Neil would be the first to say, a prime target to go back and take a look. Thank you.
Okay, we have 40 seconds for one quick question.
Stunned silence. Okay.
Yes, Bill Botke.
I can hear you, Bill. Don't worry.
All right. Yeah, but everybody else. Well, all right. No,
I'm sorry.
when we've had like nuclear bomb tests into things like alluvium, which is pretty porous, I think we don't end up with like smaller craters. I think we still got a pretty sizable crater. So how confident are you that we can really suppress crater sizes the way you want?
I'm pretty confident in that. We've done a detailed analysis. I mean, one of the things is, yeah, this is a short thing here, so I won't go into detail. But if we take a look at the characteristics of the mounds in the Mare, okay, you can see a very distinctive discrepancy between them and the surrounding areas, and there's virtually no way you could get them to be 4 billion years later. And also in the Ina mounds and the ones we see in Sosigenes, et cetera, you see crater morphologies which are much more like you would expect from an aerogel, like pit craters, and then also other morphologies that would evolve from that. So I'm pretty confident. And two, when we look at the area, some of the craters that are on the adjacent area at the edge of these things, it also shows a fundamental difference between the two characteristic substrates.
Thank you. Thank you, Jim. Okay, let's get ready for our next talk, which is by